and in the phenomenon, the magnet somehow is, after you release it, it's trapped near the bottom of the. These two seems to be inconsistent with each other, right? Because if energy is really conserved, then when you release the magnet, it should have enough kinetic energy to escape to the other side again, right?
But in the theory part, we did not consider the vibration of the string, because when the magnetic on the suspended from the string is closer to the base one, the magnet, let me rephrase it, the line will have an inertia wants to go forward, but the base magnet will attract the suspended magnet, making the spring move over, but the magnet is like didn't move that much, and will cause the vibration.
But if energy is conserved,
yeah,
it
so,
should have enough
but
kinetic energy to escape, right?
Yeah. So through it goes back up and many times of this. You can see that in the picture, the total energy we calculated have some vibration there. So I think that is mainly caused by this and make that the energy will last through time, right? So though the velocity goes down here, cannot compare the potential energy between these.
Let me turn to the opponent. Do you agree with what the reporter said?
Is that a spring?
Whether the threshold, the existence of threshold velocity suggests that there seems to be some.
I don't agree.
You don't agree. You think there are some energy loss.
Yes.
Okay.
Yeah, I think there is something energy loss as well.
Okay.
So turn to this single case, just a single magnet. Is it possible to maintain a periodic motion in the case?
You mean attracting or repelling?
Well, either way.
I think in repelling it will not converge to a same periodic motion, because we haven't calculated lambda here.
No, is it possible to have a periodic motion?
Is it possible?
Yeah.
Yeah, I think it is possible. If it's, the initial condition is strictly conserved here. Okay. Yeah.
So what's your opinion?
I don't really think there is a repair like motion, because you mentioned that this is irregular. So if it is irregular, it means it's unpredictable. So if it's unpredictable, I don't really think we can get a periodic motion to explain the motion of.
So you think even just in the case of a single magnet?
Single magnet. Single magnet may have periodic.
Can you repeat your question again?
I'm saying when you have a single magnet, is it possible to have a periodic motion of the
Periodic
reaction?
motion?
Yeah.
Periodic motion? I think it won't.
So I have a kind of complicated question for the reporter, but I would like the other teams to comment on that. So just show the air drag part slide quickly. So just for clarification, you know air fluid mechanics. So that drag coefficient times the velocity square. That's a typical drag term effect people use it in engineering. So, but you need to estimate whether if this formula, I will not say equation, this formula, empirical formula is suitable or not. Have you checked that? Okay, so that's fine. I just want to verify. Yeah. So okay, so let me switch to my main question. So in a one magnet case. You claim that in one of the slides, I think the page 27, you claim that the energy is practically constant, as conserved, right? Yeah. Okay. Yeah. So of course, it will not be perfect, but you can still see slight dissipation, energy dissipation, right? But then that's within 4 seconds. But for the two magnet case, you can show the trajectory. X or Y, right? for the two magnets. I just don't understand. So for X and Y projected separately. You see in one of the slides, I think it's one of the slides, page 35. And also, you also claim that eventually the magnet is stuck to the one of the bottom magnet. That means energy is actually lost. Yeah. So the next one, there's a slide where you show X and Y, and then eventually that they oscillate around. Not probably the next one. Yeah, for that one. See the X and Y both become static in 7 seconds. That means you have a kind of unusual large energy dissipation. Am I right? And so how do you explain that for this? This is one magnet, right? So the physics should be the same, right? Regardless of whether it's attractive or not, right? But then how come you can see this kind of unusual energy dissipation?
Yeah.
So you guys can comment after.
For the energy loss part, because we only want, because we read a paper and they say that it's chaotic, so we don't want to investigate what will happen after a long time interval. So the energy conservation is actually only fitted when in a short time interval. So when the total energy, so when this expanded like to 7, when it will not cut, like it will not be a reductor due to energy losses. So here we say energy conservation only in a short time interval. We want to calculate it when it will stop. So we use it to say that when it's in short time interval, which means that when I give a small initial potential energy, like I release it only this high. Oh, sorry. Like the energy conservation only fits in short time intervals, not all the trajectory. All the trajectory after in this specific time, it will be chaotic.
Okay, so I think that the report only mentioned that in the short time interval. I think if we take only their reports have shown energy a lot because the magnet will actually pull the magnet force to try to pull back the magnet. So actually, obviously there will be of course have energy loss, but it's maybe due to the relatively small time interval or not. We think we have to take more longer time interval to see the results of the energy change.
I think the report is still great enough, but still have something can improve.
Okay. So the scoring time. Ready? Okay. So the score for the reporter 7, 5, 7, 7, 7. The score for the opponent 5, 5, 5, 4, 5. Sorry, that's 4. It's 4. Yeah. So again, for opponent again. Yeah, again. 5, 4, 5, 4, 5. For the reviewer, 7, 6, 7, 5, 6. So let's close this session.